The afternoon session will begin within a few minutes. All the participants are hereby requested to mute their audio as well as video.
Welcome all to the afternoon session of day 2 of the 5-day online faculty development program on robotics. It is indeed my pleasure to welcome Mr. Ramesh Siyar, the resource person for the session. Mr. Ramesh Siyar, Assistant Professor, Electronics and Communication Department, Vidya Academy of Science and Technology, has been in the teaching field for more than 9 years. He did his BTech in Electronics and Communication Engineering from Vidya Academy of Science and Technology and went on to do his MTech in Electronic Design and Technology from NIT Calicut. His area of interest are robotics and automation, analog electronics, and embedded system and programming, and has published several papers in conferences and journals related to these topics. He has been a resource person for several FDPs and invited talks and has played a pivotal role in organizing several national level conferences. He is also the fellow member of All India Council for Robotics and Automation. He also serves as an certified educator of UiPath RPA courses. He has been serving as an executive committee member of IETE Kochi Center since 2017 and is also serving as a mentor for change under ATAL Innovation Mission. On behalf of organizing committee, I welcome you, sir, to the session. Over to you, sir.
Good afternoon all. Thank you for the warm welcome. Good afternoon all. Am I audible to you?
Yes, sir.
Can you see the screen which I shared?
Yes, sir.
So good afternoon once again and a warm welcome to all. So let me first of all thank the organizers of this FDP for providing me a chance to share my knowledge with you, with the participants. So I'll be handling the sessions today, tomorrow and day after tomorrow on how to apply the embedded systems for robotic application development. So my topic will be confined more or less to practical side, where I will be just focusing on how to deploy embedded system designing and its programming for developing mobile robots. So here you can see we have a wheeled robot, and the basic, if you look to the basic concept, once the structure has been completed, in order to provide some motion, we need to rotate the wheels and to add some amount of artificial intelligence. We need to gather some information from the physical world. And for that, we will be using some sort of sensors. Similarly, based on the task, sometimes we need to configure our robot to move at a faster speed. In sometimes it may be a slow process. So my session will be basically focusing on these four areas. First of all, I will be just taking you into the basics of embedded programming, what is meant by programming, and some basic concepts which is necessary for the better understanding of the remaining topics like motor interfacing, speed and direction control of the robot, and the analog sensor interfacing. So during the course of the program development, we'll be familiarizing all these things in detail. We'll be discussing about the hardware interfacing section, the designing side, as well as the programming side. So before going into the session, I would like to get some response from the participants. First of all, how many of you are familiar, or how many of you have a small flavor about what is meant by this AVA programming? Can just reply in the chat. Do you have some previous experience on AVA programming? Since we have already planned the session for a offline, in the offline mode, and we thought of having a hands-on session, I'll be trying my level best to give a flavor for that also. So any one of you have some experience on AVA programming? Anyone? So I think we have around total of have 62 participants. So no one is having the experience on AVA program. So I'll be taking you to that. The next one, how many of you are having on using your desktop or laptops? Because we are going to have the programming session through the online compiler or on the tool, that is Tinkercad, which is free for everyone to use. So I'll be explaining the codes, and we can do the simulations or emulations using this Tinkercad. Okay, so even though if you are not having this Tinkercad today, for tomorrow session, it will be better you are having that tool, or you are having that facility to do these experiments on the Tinkercad tool. Okay. So let's start the session. So day one, today we will be first of all looking into the basics of embedded C. We'll be just revising some concepts, the like basic concepts like variables, etc. Then we'll be looking into the loop programs which we'll be commonly using. We'll be using in embedded programming. Then regarding bitwise and shift operators, in the programming languages and how you are using in embedded programming and what is its significance for each of the operators. Then after that, we'll be moving on to the motor interfacing. So as we know, we need to provide some logic. We need to provide a positive logic and a negative logic, or a logic 1 and 0 to the two terminals of the DC motor. Okay, so with respect to the small wheeled robots, it is a DC motor which is commonly used for providing the motion for a wheeled robot. So in order to work in order to operate a DC motor, we need to there are two wires, and we need to provide a logic high voltage and a logic 0, or a positive potential and a negative potential. So we will be discussing about that, how you can control that logic flow to the motor terminals using the ATMEGA 328P or the AVR programming. Okay, so here the concept of or we have used ATMEGA 328P here. It's because the online compiler which we can use freely, that is Tinkercad, only has the simulation profile for ATMEGA 328P microcontrollers. It doesn't have two other high-end AVR microcontrollers like ATMEGA 32 or ATMEGA 2564, etc. So if you are understanding about the concepts that we are discussing in these 3-day sessions, we can use those knowledge in order to develop program for any of the AVR microcontrollers in the future. Okay. So first of all, when moving on to the basic concepts, first we know that embedded system is basically defined as a system which consists of a small computer or a small processor which stores some amount of software or stores some software which controls the hardware circuitry of that particular system to perform a particular given task. Okay, so if you look to the program, the computer program can be defined as a sequence of logical steps that is being performed by a computer to accomplish a given task or a certain task. And if you speak about the programming language that we make use of in computers, it's nothing but it can be defined as a syntax that has to be followed so that the computer understands the sequence of the logic steps that it has to be executed so that the task which the computer has to accomplish can be done perfectly. Okay. Now, transforming this basic knowledge or this basic concept into embedded C, it's nothing but a language which is basically an extension of the conventional C language that is being used in computers for developing programs in order to meet or in order to accomplish some task that the computer has to do. So embedded C is an extension of that conventional C language, and it uses the same syntax and semantics that the conventional C language uses. And this embedded C programming language is particularly used for writing programs or writing programs or codes that is basically meant for developing microcontroller based applications. Okay. So before going to further, if you have any doubts, you can unmute yourself and raise the question. Okay, in between. So that's the basics of the embedded C. And now we move on to the basic concept that is necessary for developing any of the programs. The main concept is variables. I hope that everyone is aware about variables in C. Similar to that itself, here also, variables in embedded C is nothing but it's an element that act as the storage containers for data. In embedded C also, if you are developing a microcontroller based application, you need to store some data in your program. Sometimes you need to provide some data to the external world through the peripheral interfaces, etc. So variable is that element which can be used as a storage container of these types of data. So basically, the data which you need to store inside the memory of the microcontroller, or the data which has to be passed to the external world, has to be initially stored in some memory location. And each of the memory location that we make use of in embedded programming always has a unique address. And we all know that when we talk about the memory, the number of bits used to define a particular memory location is not a 1 bit or 2 bit. It will be either a 16 or a 32 bit, or it may be sometimes even more. But most commonly, we go for 20 or 32 bit or 64 bits nowadays. So it is not easy to remember all these combination of 32 or 64 bit at every instant of time during the development of the program. So there is an easy method. So this variables is an easy method which you can use to store these memory addresses. And despite of using bits or the combination of the numbers, here we will be making use of some user-defined names. So in that case, we can say, in this context, we can redefine variables in embedded system as the elements that is used as a substitute for storing the memory addresses with user-defined names. And as you can see, the basic syntax of the variable is defined as data type followed by the variable name or the user-defined name. So here the data type defines what is the length of the data that this particular memory location has to store. So the common types of data that we use in embedded system are integer data type. In several sensor cases, we go for the floating type. And when we try to interface some LCD or some 7-segment display units, we go for the character. Okay. So this has a higher significance in embedded system, basically. Because if if you're getting some data from the sensor, and that data, if that data can be stored by using 8 bits of the memory's location, we need to use the variable corresponding for storing that particular data as an integer type. Because if you go for a float type, it normally makes use of 32 bytes. Okay, it will be of higher bytes. Okay, there will be 32 bits, not bytes, 32 bits basically. So the you need only 16 bits or 8 bits for storage. So out of these 32 bits, you are wasting the remaining. You need only 8 bits for storing that particular data. But instead of that, if you go for the floating data type, you are going to use 32 bits of your memory location. So this comes into play when we go for developing an optimized embedded applications, especially even in robotics also, not only for robotics, for every embedded applications. This is a main criteria, because we know that nowadays our students in the institutions, when they do their mini project or micro project, they will be going for purchasing some microcontrollers like Arduino Uno boards or mega boards, nano boards, etc. And if you look for some Arduino boards, they might be having like the Arduino board that is been fabricated and marketed by India, that is Freedino. It normally has ATmega 168, that is, it has 16 bytes of memory. And if you go for the Arduino Uno version, which is being marketed by Italy or any other countries other than India, they commonly has Arduino 328. So when the students go to the market, they say that, okay, it is compatible. It's compatible, but on the memory side, there is. So sometimes the student only needs 8 bytes of memory. So in that case, or 16 bytes of memory, in that case, he need not go for this Arduino Uno or ATmega 328. Okay, so likewise, they can have a optimized decision on selecting the microcontrollers. Similarly, by knowing the amount of bits required for storing a particular data, if they are assigning that particular specific data type or the exact data type for each of the variables that they are using, they can save the memory, and so that they can use this limited memory microcontroller for implementing the same applications. Okay, where it has been implemented on ATmega 2560. So whatever be the program that we are doing today in these 3 sessions, we can do it on any other boards like Admega 8 or Admega 168 or any other, even on Admega 256 also. Okay. So you can see that variation. So we will be doing some simple examples which gives you the proof. Okay, you can show that this to the students as a proof that this, if you're using this variable of integer data type, you need only 8 bits or 16 bits to storage, that is 2 bytes. If it is a character type, you need only 8 bits, etc. Okay, so I'll be taking you to that particular session also, so that you can show that experiment to your students and they will be convinced. Okay, or you can show that in mind. Okay. We will be going to that. Then we have the loops is the next common thing that we commonly use in embedded C. So loops is nothing but the concept which is used to execute a group of statement or a block of code or even a single statement multiple times. Okay, so you need to perform this particular execution of this a particular statement or a group of statements or a block multiple times. So in that cases, we make use of the concept of loops in embedded C. So if you look to the basic structure, initially you will be starting. Starting means in order to keep track of the count of how many times this particular statement or the block of code has to be repeatedly executed, you need some variable to store that value. So the start is the point where you will be declaring or initializing that particular variable. Then we will be going for the condition check. So if you will be checking the condition. Let us say that you need to execute a block of code for 6 times. So initially you will be initializing that 6 to a particular variable. Then you will be checking the condition whether the variable count value, currently the value that is stored in the variable is less than 6 or not. So if it is true, it is less than 6, then that certain block of code has to be executed. And once it is found true, the block of code is executed and it again come back to check the condition. So again, next time again it is been checked, and if it sees that the condition is still true, keeps on executing. And once it finds that the condition is turning false, that is a variable value is not less than 6, it has been gone beyond 6, then it is creating a false statement, and you will be exiting from this particular loop structure and you will be executing the remaining parts of the program. Okay. The two common loop formats that we use are while loop and for loop. So this is the basic syntax of while loop. We have the while followed by the conditions in the curly bracket, the circle brackets. Then inside the curly brackets, you will be writing the block of codes. So in this, it checks for the condition which has been mentioned. If the condition is true, then only the block of codes is executed. Okay. If it is false, then the execution will be skipping this block of codes and it will be going out of the curly brackets. So the immediate line after the curly bracket, closed curly bracket, will be executed. So a small modified version of this while loop is known as the infinite loop, where the condition is always true. So in this case, you will be executing the program infinite times. There is no condition which makes it false. So if I write in the embedded C while true, it makes the execution of this block of code into infinite times. Most of the codes which we see, you can see that we use this while loop, where it is while of 1. Okay, instead of writing true, I can write 1. If I write while 0, that is while false. Okay, so if that condition is always while false, it is not going to execute. So the peculiarity of this infinite loop and while loop is that only if the condition that is mentioned inside this bracket is true, the block of code will be executed. Then we have the for loop. In for loop, the basic syntax is as follows. We have for. First statement is you need to initialize the variable which is going to control the entire execution of this looping structure. Then we need to mention the condition of check. Then we need to increment or decrement the variable. So these three elements are mandatory. If you're not using any one of the element, it may not be workable in all the systems. So it depends upon again the compilers. Okay. So if I'm not mentioning any initialization step, there is no condition and there is no increment or decrementing operation, then your for loop will be acting in an equivalent way of your infinite loop. Okay, that is, I'm not initializing any variable, I'm not mentioning any condition, I'm not mentioning any increment or decrement operation. I'm just writing two semicolons inside this brackets, circle brackets. Okay, so in that case, for inside the circle brackets, you will be having two semicolons alone. So in that case, it is working as an equivalent looping structure to this infinite value. Okay. So once the variable has been initialized, then it goes for the condition check. Then it comes to, if the condition is true, then the block of code is being executed. Then this increment operation, which is mentioned inside this circle brackets, will increment or decrement operation that is been executed, and the condition is rechecked. And if it is true again, then the block of codes is been executed second time. Okay, so initial or the first time when the for loop is executed, only these two steps are being executed, that is initialization of the variable and condition check is executed. Okay, and after the block of code is executed once, then it goes to the increment or decrement operation of the on the variable, which is mentioned inside your for loop based condition. Now we have the bitwise operators. So bitwise operators, it's sometimes known as the logical operators in our programming language. Logical operators means logic and, logic or, XOR operation, not operation, etc. Okay. So in almost all the microcontrollers, these logical operations are executed. When they are being executed, they executes on bit by bit. That is, if I have an 8-bit data, each of the bits of the 2 bits, if I need to perform an AND operation, I need 2 datas. Just 1 minute, let me share my entire screen. So I hope that, can anyone respond whether you're able to see the whiteboard?
Yes, yes.
So if I have an 8-bit data, let us say, let me take an example, 1 0 0 0 1 0 0 1. Okay, so if I need to perform a logic AND operation, let us take an example of AND operation. I need 2 inputs A and B. Okay, so let this first 8-bit be denoted by A, then the second bit be B. So let us take the data is like this. Okay, so when I perform AND operation between these two data, effectively in the internal of the controller, each of these bits, the first LSB, initially the LSB will be logical AND operation between the LSB is executed and the result is been stored. Okay, so 1 and 1, you will be getting 1, then 0 0 0 1 0 0 0 0. So likewise, internal to the microcontroller, when you are executing the logical AND operation on these two variables A and B, each of the bits, if thus A is an 8-bit data and B is an 8-bit data, in that case, each of the bits are being executed. So this is more seen in our microcontroller applications, because when we go for the embedded programming, we make use of several registers where we will be storing the data for controlling the speed of the robot, etc. For all the applications, we will be making use of several registers, specifically these registers are known as special function registers, because we are going to interface some motor, or you're going to interface some sensors, etc., to your microcontroller. So this connection or this interface between the peripheral and peripheral devices, that is your motors or sensors, and the microcontroller, can be established through the special function registers. Okay, so all these registers will be either 8-bit or 16-bit. So with respect to our ATMEGA 328P, which is of consideration in our discussion, all the registers are 8-bit data. Sorry, 8-bit data. So when we perform logical AND operation between two 8-bit registers, each of the bits of the registers are taken and bitwise logical operations are performed. Okay. So if we come back to our slide, you can see if I perform a bitwise AND operator, so I can have 0 or 1 as the data. Okay. So if I am performing a logical AND operation with any of these 0 or 1, and the other data, one of the data can be 0 or 1 and other data is always 0, then the resultant is equal to 0. Okay, but if the data is 0 or 1, there are two data, so one data is 0 or 1 and the other data can be always 1. In that case, it is the same data itself. So this means if I need to make some bit locations of the register as 0, then what I can do is that which is the bit that I need to make a 0, I can just make that bit as 0 and remaining bit as 1. Okay, so this can be made more clear to you. So if, let us take a small example, I have a register value 1101100. Okay. So let us assume that these are the 8 values corresponding to a port. So we have a port, that is a group of pins to which you are connecting some LED. Okay, so I am having 8 LEDs connected to the port of the microcontroller. Okay, 1 2 3 4. Okay, so I am storing these values. Initially I'm having this value. This means the LED. So in the yesterday's afternoon session by Regu sir, he has told about the drive system, that is logical VOH and VOL, everything pull up, pull down, etc. Okay, similarly logic high driven systems and logic low driven systems. So I am discussing about a logic high driven system, that is when I'm writing logic 1 to the pin of a port, the LED connected to that particular pin will be turned on. Okay, so here this LED is on, this LED is on, and this LED and this LED. So there are 4 LEDs on. So after an instant of time, if I need to turn off only these 2 LEDs, okay, I need to turn off the LED that is connected to the, normally we say pin 0, pin 1, pin 2, pin 3, pin 4, 5, 6 and 7, that is 8 pins. Okay, so after instant of time, I need to turn off the LED that is connected to pin 2 and pin 6 of my port. Then what I need to do is that I need to logically AND this port value with value such that only those bits can be 0. Okay, remaining bits I can keep it as 1. So if I perform a logical AND operation with this previous data with the new value, that is 1011 1011, if I look, I can see 0 0 0 1 0 0 0 1. So if you compare, you can see this was the actual value, that value and the resultant are same. Second bit is again same. The third bit has been changed. Okay, fourth bit is again same, fifth is again same, sixth is again same, not the 6, 50 is okay, that is 5, then 6 is changed and 7th is also same. That is only those desired bits which I need to change has been changed to 0. Okay, so this is the significance of the bitwise operators. So in embedded C applications, especially in robotics also, we need to specifically change the status of some of the pins to 0 or 1, or you need to complement those values, etc. Okay, so with respect to those specific demands, we will be applying these bitwise operators in our embedded C application. Okay, so whenever I need to make some selective bits of a register or a port as 0, I can perform the bitwise AND operation. If I need to make some selective bits alone as 1 from the previous value. Okay, so in that case, I can go for the bitwise OR operation. Okay, then in some cases I need to complement some selective bits. Okay, so in that case I can go for the bitwise XOR operation, keeping the other bits as unchanged. Okay, there is no change for the other values. And the other next common operator is the complement operator. So there's a small mistake here. It's not bitwise OR, it's complement. Okay, so that is used to make selective bits as 0. Okay, so there's a small mistake here. That is basically the last one, that is bitwise complement operation is used for complementing the value of the bit. Okay, there is no multiple inputs. So if I have 0 as the initial value, if I need to change into 1, I can perform the bitwise complement. If I have 1 initially, if I need to change that bit alone to 0, then I can go for the bitwise complement operation. Okay, so this complement operation can be done not only for a single bit, it can be done for a register also. Okay, but effectively in the internal execution, it will be carried out in a bitwise manner. Okay, then the next common thing that we use or that we encounter in embedded programming is the right shift and left shift operators. So if you have 2 greater than symbols, it corresponds to right shift a bit towards right to single bit. Okay, so here you have the initial value 1000, then 1110. If I need to shift 1 bit towards right, I can perform this particular right shift operator. And if I need to shift leftward, then I can use the left shift operator. Okay, so this will be more clear when we do the programming side. Okay, so these are the common things that we will be using throughout in our programming or in throughout the sessions in the 3 days.
मी सकाळी नसतोय उद्या, मी बुधवारी नसतोय, जतवाडला असतोय. जरी उद्या टाकलं की नाही ये मी, तुम्ही जावा, तुमचं असलं ठीक आहे. उद्या
okay, so moving forward, now let us move on to the ATMEGA 328. So I use the pinout of ATMEGA 328, which combines the pin mapping with the Arduino Uno board, because in our Tinkercad we will be making use of the Arduino Uno board. Okay, so you will be having that layout. So you need to read that layout and transfer that information into our programming side. Okay, so in Arduino Uno, you will be having the right side of the board with digital pins. So that is these digital pin 11, 9, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and zeros. Okay, on the left side of the Arduino board, you will be having the analog pins, that is A0, A1, A2, A3, A4, A5. Okay, so if you look to the internal diagram or the pinout of the IC, that is the controller that ATMEGA 328P, you can see that corresponding to digital pin 9, we have PB1. That means port B1. So if I have a port, I have an 8-bit port, so I can designate each of the bits of this port as 0th bit, 1st, 2nd, 3rd, 4th, 5th, 6th, and 7th. Okay, so if you look to this, you can see that the first bit of the port B corresponds to the digital pin 9 of the Arduino Uno board. Okay, so this is having that importance in that particular thing. So if you look to the overview, so basically this ATMEGA 328P is a 28-pin microcontroller that is commonly used in Arduino Uno boards. And if you look to the pin out, here you can see this is a 28-pin structure. So we have VCC ground, that is 1, 2, again a ground pin is here, then analog reference voltage and analog VCC. Okay, so 1, 2, 3, 4, 5. Irrespective of these 5 pins, all other pins are serving as some applications in accepting some data or outputting some data. Okay, so out of the 28 pins, we have 5 pins for providing some potentials. So out of the 28 pins, we have 23 pins which can be used as input or output pins. Okay, that is one of the feature, and each of these input and output pins can be programmed individually. Okay, that is another feature. And the other feature is that it has 2 8-bit timers or counter with separate prescale and compare mode and 1 16-bit timer. So we will be covering this topic with respect to what is meant by timer and counter, and we will be doing some programs on the 16-bit version of this timer in tomorrow's session. And it has some it has an inbuilt real-time counter for mounting the time with separate oscillator irrespective of the common oscillator at which the controller works. And there are 6 PWM channels, and we will be using this concept of PWM, or we will be using this PWM feature for controlling the speed of a robot. Okay, so that we will be again discussing on the session day after tomorrow. Okay, together with the feature of how to access the ADC, so that an analog sensor that is interfaced with your robot can be processed. Okay, the data can from the analog sensor can be read and it can be processed for performing some specific applications. Okay. Now, next is how to access these ports. So, as I told, if you look to the pin out, here you can see we have 23 pins which can be used as IO lines. Excuse me, anyone has some doubts?
All participants are requested to mute their audio if you don't have any doubts.
Trial version.
ਕਿਹੜੀ ਗੱਲ ਦੱਸਦੀ ਮੈਨੂੰ ਵੀ ਦੱਸ ਦੋ ਮੈਨੂੰ ਪਤਾ ਲੱਗੇ
Okay.
So you can continue.
Out of this, okay, thank you, sir. So out of this 23 pins, if you look to the nomenclature, you can see pin number 23, 24, 25, 26, 27, 28, and pin number 1 is designated as PC, PC0 to PC6. Okay. Then from pin number 2, 3, 4, 5, 6. Then we have 11, 12, and 13. That is PD0, PD1, PD2, PD3, PD4, D5, D6, and D7. So they are grouped as some group with D. And remaining pins PB0, PB1, PB2, PB3, PB4, 5, 6, and 7.
Ramesh sir, it seems your phone has been muted. Can you unmute?
Sorry. So as we see, we can see on this particular pin mapping, here you can see several pins. So that is from pin number 23, 24, 25, 26, 27, 28, and pin number 1. They are being grouped to C. And some of the pins, that is pin number 2, 3, 4, 5, 6, then 11 and 11, 12, and 13, they are grouped as D. Okay, that is 0 to PD0 to PD7, and the remaining pins to B. So in that, with respect to this, we can say that this ATMEGA 3 to 8 is a microcontroller which has 3 ports. Okay, that is the total 23 IO lines which is available for us to accept some input or give some output, are grouped into 3 groups, that is group C, D, and B. And if you look to the nomenclature, you can see under the C group you have only 7 lines, that is 1, 2, 3, 4, 5, 6, and 7. Okay, And if you look for D, that is D0, 1, 2, 3, 4, 5, 6, 7, 8. So in group D, we have 8 lines. For similarly for group B also, we can have 8 lines. We do have 8 lines, that is PB0, 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so with respect to that, we can generally say that our ATMEGA 328 has two 8-bit ports. Okay, there are two groups, that is group B and group D, which are having 8 subdivisions or 8 lines under that particular port, and group C is the only port which is having 7 bits. So if we move from this ATMEGA 328 to ATMEGA 2560 or ATMEGA 168P or any other versions, you can see that this number is going to change. Okay, for example, in case of ATMEGA 2560, you can see that you have around 3 ports which is having 7 bits. So here we have only port C. In that case, we will be having another 2 more ports. Okay. Similarly, the number of ports which is having 8 bits grouped together is also more than the ATMEGA 328. So once we understand how to program the ports or each lines of the ports of ATMEGA 328, we can use this same concept, or you can extend the same concept to ATMEGA 2560 also. Okay. And so another feature is that all the port pins, each of these group can be configured individually as input or output. That is, out of the 8 bits of port B, depending upon the application, I can configure either the 4 pins can be input. Okay, that is 4 pins of port B is going to accept some input values. Other 4 pins is going to accept some output, is going to give some output values. Okay, so there is a flexibility to individually configure each of these pins. Okay, so this feature may not be applicable to all the microcontrollers. Okay, in some microcontrollers, the data sheet of the microcontroller, the manufacturer itself says that out of the 4 ports which is available for the microcontroller, only these ports can be individually ports has the pins which are individually programmable. Okay, that means in that case, only those ports can be accessed individually. The other ports need to be accessed, or we need to program them as a group of 8 bits. Okay. Now, in order to access these pins of the ports, we need to access some registers which is internal to the microcontroller architecture. Okay. So those registers are normally known as special function registers. Okay. So likewise, with respect to any of the microcontrollers, whenever we need to establish a peripheral interface with the pins of the microcontroller, you need to configure some registers. Okay, so that such that the functionality of that interfacing can be established successfully. Okay, so those registers which is responsible for establishing a particular peripheral interface of a microcontroller is known as special function registers. So for accessing the general purpose input or output lines or ports of the ATMEGA 328, we have 3 registers associated with them. That is DDRX, port X, pin X, where X can be B, C, D. So if I need to access, I'm only going to access the B pin of B port, then the register name will be DDRB, port B, and pin B. If I'm going to access D, then the name will be DDRD, port D, pin D. Okay, likewise, it will be changing. Now let's look into what does these registers mean. So first one is DDRX, that is data direction register. So as we told, each of the lines of the port can be used for accessing some, reading some value from the external world or providing some data to the external world. Okay, so when your port pin is going to read some value from the external world, it should act as an input source. It is going to it is acting as an input pin. Okay, so that it can accept the value from the external world. So in order to configure that, we need to load 0 to that particular location. Okay, so if I have, so we know that we have an 8-bit port. Okay, so let us consider port B, for example. So since it is an 8-bit, this register DDRB is an 8-bit register. So it can store 8 bits inside it. Okay, so 0th bit 1, 2, 3, 4, 5, 6, and 7. So this 0th bit corresponds to PB0. Okay, this corresponds to PB1, and the last one corresponds to PB7. Okay, so if I need to read some value from the external input, external peripherals, and that peripheral is connected to PB0 and PB1, I need to write 0 to these locations. Okay, and I'm having some LEDs connected to PB2 and PB3, then I need to write 1. Okay, so this is how I need to configure. Okay, so if I look to take this example, I need to make the lower nibble, the lower 4 bits of this particular port B has to be made as input pins, and the upper 4 bits as output pins. So I'm writing 0 to those input locations and 1 to those output pins. Okay, so together with this, if you look, the values as per the given example was lower 4 bits as input. So I'm writing 0 and upper 4 bits as 1. Okay, so if I group this is 0 and this is equal to F. So to this register, I need to load the value DDRB equal to 0xF0. That is a hexadecimal value. Okay, you can also write DDRB equal to 1111000 in our programming. That's not an issue. In embedded C programming, you can go for this binary format or you can go for the hexadecimal format. Okay, so but following the hexadecimal is the most convenient method because it is easy for us to decode it. Okay, so generally or commonly we'll be going for this hexadecimal. Okay, and very rarely we can see some of the people are going for this binary format also. Okay, so if you look to this definition, you can see that 0 corresponds to input and 1 corresponds to output. So here we have a small question which we can use to evaluate the students whether they know about this concept clearly. As we all know that by default, whenever we turn on a system, all the memory space will be resetted to 0. Okay, so here when this register location is resetted to 0, it means all the pins of the ATMEGA 328 will be by default acting as input pins. So that whenever you need to configure this register in order to make that particular pin as an output. Okay, so by default, so if we ask the student what is the default state of the pin of an ATMEGA 328, if he or she says it is output, it gives you an indication that he or she is not clear about the basic concept. Okay, you can use these small tricky methods to evaluate your students. Okay, moving forward, the next register is a port register, that is port X. So this register has two functions. When you are configuring the port or the port pin to act as an output, this register port X is used to define the data that the microcontroller is going to pass to the peripheral device. Okay, so when it is an output port, it will be, if I'm writing 1 to that particular location, that pin will be giving a logical out at to the peripheral device. Okay, as input to the peripheral device. And if I'm writing 0 to a particular pin location or a bit location, then it will be sending logic 0 to the peripheral device. Okay, so here you can see an example, port D is loaded with 1. That means all the pins will be giving logic 1 as the input to the peripheral device that is connected to the port D pins. Okay, when your port is acting as an input, okay, in case of an input, as discussed by Raghu sir yesterday, whenever you are configuring the microcontroller pin as an input, you should take care to define a stable state for that input pin. Okay, so if I'm going to connect a sensor, I should not, the program should not read some wrong answers. Okay, so what you need is that you need to define a stable value initially, and whenever that value is being changed, then your controller will be informed and it will be reading those sensor values and it will be processing and performing some task. Okay, so in order to ensure a stable state in any digital logic, we make use of this pull up or pull down configurations. In most of the microcontrollers, we have internal pull up circuits integrated, and when your port pin of the ATmega 328 is being used as an input pin, you can use this port X register for activating and deactivating this pull up feature, which is integrated inside the ATmega 328. Okay, so when you are making the pin as an input pin using the DDRX register, if I am writing 1 to that particular pin in the port X register, it activates the pull up circuit that is integrated to that particular pin. Okay, and if I'm writing 0, it is going to deactivate the pull up. So in that case, if I'm preferring for a pull down circuit, I need to provide that pull down circuit external to the controller board. Okay, so here I am making all the pins of the port D as input, and I'm going to activate all the pull up to all the pins of the port D. So I need to write 1 to all the values. So if I have the condition like this in a program, if I have a statement DDRD equal to 0x00 and port D equal to 0xFF. This means all the pins of D are input, and this has activated pull up circuitry. Okay, this has activated pull up circuitry to all those pins of the port D. Okay. Then the last register is pin register, which is used to read the data that is present on the port X pin. Okay, so corresponding to each of the port, you have several pins, and what is the current data that is present on that particular pin of the port? We need to read it for some applications. I can use this pin X register. Okay, so I just need to read what is the content that is stored in this particular register and save it to some variables. Then I can get the information about them. So here I have port B with a current value 111000. Okay, so this is F0 is a value. So if I need to read this to the memory of the microcontroller, I can read the pin X. So that is X is equal to pin B. What it performs, it will be on executing this text, this statement, the value of port B will be read and it will be assigned to the variable X. That is a memory location. And once you read that memory location, you can see that the value is 0xF0. Okay, so this is used when we go for the input circuitries, etc. Okay, digital input most probably. So now we can have a small exercise. So can I have an input from the participants, whether you're clear with the concepts which we have discussed till now? Or you're having any doubts?
Participants can unmute themselves and can talk.
Small response, whether you're having any doubts or you're not having any doubts. Some response.
You can either unmute your mic or you can send through the chat that everything is clear or not. You have received 2 messages saying no doubts.
No doubts. So I'm moving forward.
Okay, sir.
So here the task is that I need to turn on this buzzer on LED. So we will be doing the experiment initially for the LED, then we will be drawing the circuit for the buzzer right now. Okay. So here we have the microcontroller at ATmega 328P, and to the third pin of the port C. Okay, I have C, B, and D. So to the third pin of the port C, I am connecting an LED. Okay, so I need to turn on the LED for 1 second, and I need to turn off the LED for 1 second. Normally we say that this is a blink example. Okay, so whenever we attend any of the microcontroller training programs or workshops, this is the first experiment, blink an LED. Okay, so here we are going to blink this LED, and for this we are going to use the embedded C program. Okay, so there are several sections which you can use in general. The first section is the header files sections. Okay, header file or include. It is normally known as the include section. Okay, so there you will be including, or you will be mentioning the files which has to be included for the compiling and assembling purposes of the entire program perfectly. Okay, so sometimes it may be some header files, sometimes it may be some associated continuous files, etc. Okay, then after that we normally say that that is a function definition. Okay, in case of embedded C, it is less recommended to use global variables. Okay, those of hope that everyone is familiar to programming basics. So in programming basics, we have the variables defined in global level and local level. That is global variable and local variable. So in embedded C, the concept of local variable is commonly used. Global variable is very rarely used. It's because when we go for global variable definitions, we are assigning the memory space permanently. Okay, so that sometimes that particular memory location needs to be used only 1 or 2 times. Okay, so in that case, just reserving the memory for the lifelong of the system is not a good process. Okay, so most of the cases we'll be going for the local variables. So that is not in general C programming. Before this function definition, we'll be having the global variable definition and constants, etc. So here we are not practicing that. So here followed by the include section, we have the function definition, where you will be declaring and defining all the functions that has to be executed to accomplish the given task by your embedded system. Okay, and at last you will be having the main program. Okay, so this main program will be having calls to the functions which has to be done. Okay, so if we look to this given example, here we need to make this particular pin as an output. Okay, so that is one of the function that we have to do. Then we need to supply some value through this pin so that the LED connected to this pin is turned on. Then we need to supply some value to this particular pin so that the LED will be turned off. Okay, so these are the 3 functions. So your main program will be having 3 functions. One is the function to make PC3 as output. Okay, that is a one-time function, and you can have some infinite while loop where it will be having functions to turn on the LED, and you can have some function to turn off the LED. Okay, in between you can add the delays. Okay, and these functions will be defined in this particular area. Okay, so we move on to that program first of all. So in the initial include section, we have to include basically 2 header files. One is the header file corresponding to the AVR microcontroller. Okay, so all these information regarding the special function registers, its operating frequency, everything, it will be included in this AVR io.h file. So you need to include #include AVR io.h and the standard IO operations for enabling the standard input and output operations. It is not necessary here, but normally we used to write this so that all the mathematical operations, etc., if you are using the program like some multiplication, etc., is there, it will be done automatically. Okay, so these are the 2 mandatory header files which we need to add. Okay, before to this, there is one more line, that is you need to define the frequency of oscillation. Your Arduino board will be normally connected with a 16 megahertz crystal, but we can change that 16 megahertz to some 4 megahertz or any other possible frequencies which is been allowed by the manufacturer. Okay, so if there is a change, we need to define that frequency, CPU frequency, so that the exact timing will be there. Okay, so for today's session, we need not concentrate on that particular area, so we are not writing that here. Then, as I told, the second section is a function. So first of all, I need to configure the pin. So for that, I am writing a function known as void port init. So this is a user defined name, initialization of the port. So I need to make the port pin 3 of port C alone as output. Okay, so if you look to the register, we have the DDRC register, which is an 8-bit register, which you already decided. So this is 0th bit, 1, 2, 3, 4, 5, 6, and 7. Okay, I need to make the PC3, that is, this bin has to be made output. So I need to write 1 to here. All other bits can be kept in the default status. Okay, so if I group this is 8 and this is 0. So I need to write DDRC equal to 0x08. Okay, I can initialize the value to 0 in it first of all. So I need to write port C equal to 0x00. Okay, so these are the two statements which I need to define inside the initialization function. Then to turn on the LED, I need to write just port C equal to 0x08. That is, I need to write 1 to the port X register of C, so that it will be turned on. And if I write 0, I can write port C equal to 0x00. Okay, so that is what I have defined here. Initialization function is there, DDRC equal to 0x80, port C I have initialized as 0x00. Okay, now to turn on, I have written a function known as buzzer on. Okay, so in that, sorry, I just changed the function, that is port C equal to 0x00, that is 0x80, that is to turn on. Okay, I need to write a logic 1 to turn on the buzzer. So logic 1 should be written, so that is 0x80, and to turn off it should be 0x00. Okay, so here I have just written the opposite statements. So when I'm calling this function, it is going to turn off the LED, and when I'm calling this function, it is going to this is off and this is on. Okay, opposite action happens here. Okay, so that will be making the correction. Now when we go to the main program, you can see the main program starts int main. Okay, always it will be returning. So here the void which is written before the function name means that when you call this function, it has been executed and no value is being returned, and this word inside the circle brackets indicates that there is no argument. Okay, so in case of main, it should be always int. It's because whenever a return 1, okay, after executing this program, and if there is a return 0 statement, it shows that there is some error in between. Okay, in some compilers it may be return 1, and in some compilers it may be return 0. Okay, so here for Atmega 328, if it is return 0, it indicates inside the main program or your task has not been executed completely, there is some error. Okay, so to get that particular 1 or 0, I am writing this return values integer. Okay, so 1 or 0 will be returned. Then there is no arguments to this particular program. So once it enters, I need to initialize the port only for once. So I'm writing port initialization before the infinite while loop. Then I'm entering to the infinite while loop, and I'm going to write buzzer on, that turns on the LED. And we have the inbuilt delay functions. Okay, tomorrow we will be writing these functions for our concern and with exact durations, okay, using the timer. So today we are going for the approximate delay. So we have the inbuilt functions underscore delay underscore ms 1000, which gives you 1000 milliseconds, that is 1000 into 10 raised to minus 3, that is 1 second. After 1 second delay, we have the next function which turns off the LED, and again 1 second delay, and this keeps on executing. Okay, so when a layman, so if you are the developer and you written a big code, and on the next day a new person joins your team, and if he or she just reads this main program, okay, using these names nomenclature, you understand that okay, the first step that is been done in this program is to initialize the port. Okay, so if he or she goes to that particular definition, they will be getting the clear definition for what is being done by this port. Okay, then on seeing this, okay, this is going to turn on the buzzer, this is going to turn off the buzzer. So what is happening inside need not be conveyed to the layman suddenly. Okay, in the initial stage, the layman is getting an idea that this program is meant for performing these applications. Now, if he or she is interested to make some changes inside this program logic, then only he or she has to go to the definition of the functions and analyze those concepts and do the necessary changes. Okay, so this is a best way to practice embedded C program development, etc., development and embedded programming, so that it is very easy for anyone to debug. Okay, at any stages. So that's about the theory, and now we can go on to the practical side, whether the participants are clear with the program and the logic flow which I have explained. Then I can move on to the simulation side. Shall I move on to the simulation side? Someone please respond. Yes,
Yes, sir.
we
Yes, sir.
can use the same code for another controller. Means inside the AVR microcontroller family, you can use the same code. Okay, it's because the name nomenclature of the registers, etc., will be common for most of the AVR microcontrollers. Because port C will be C, port B, port D is available on ATMEGA 32560, etc. Okay, but if you move on to some 8051 or if you move on to the big microcontrollers, etc., the nomenclature of this special SFR will be different in one sense. The other chance is that sometimes the logic here, if I am writing 0 to DDRX, it means that the pin is acting as input. But in some PIC microcontrollers, if I am writing 0, it is going to act as an output pin. So those changes should be taken care, but the logic wise will be same. Okay, so let me take the simulation side. Okay, so for simulation, we will be using this Tinkercad, which is a tool from the Autodesk. So you can just type on your browser tinkercad.com, and you can use this sign in option. Okay, you can just click on the sign in. Either you can use your registered, you can join register separately, or you can use this your Google account. So I'm using my Google account directly. So I'm using my Google account, and I'll be landing in my home page. So this is my home page. So there are multiple functionalities for this Tinkercad online simulator. You can use this Tinkercad for developing the 3D designs. Nowadays we are more popular to the 3D printing, etc. So if you need to create some 3D design, you can use. Then I have the circuit section. Then we have the code blocks, which is mentioned for coding applications. Okay, so I can use the circuits here. So let me give you a few minutes so that you can create your account, and you can come to this particular page. Okay, once you are ending up at this circuits, you can click on this create new circuit. So that you will be ending up at this particular page where you will be getting the workbench area, etc. So this depends upon the internet facility. Sometimes you may be getting very fast, as well as the system resolutions. Okay, so here you need to just first of all search for Arduino Uno. Okay, so you can see that board, just to drag here. Okay, so that's a new component. Okay, now to just drag here, you can give your any name of your wish, and you can see a tab known as code. Click on that. So here there are two types of programming, that is by using the blocks, but we are going for embedded, so I'm using the option text. Okay, so here I can write the program which I have explained. Okay, so I'm typing the program. Okay, just 1 minute. TRC equal to 0x8008. Sorry. Or C equal to 0x00. That the function is completed. Void LED underscore on. That instead of the buzzer on, I am using LED on here. It is port C equal to 0x08.
यार तुही एक घंटे पे जो बंदा बाहर चलो चलिए सर 12 बजे ना चलो मेरी टेंट ला दोगे फिर मैं सेशन आउट कर दा इथों
Just copying this, so for instance I can type it. Okay, so once I complete this, then I need to keep on LED also, so I'm typing LED. Inside this I need to have an LED also. Okay, so I have an LED here, so I can drag it here. So that is PC3. Okay, PC3 means it is the analog pin 3 of the controller. Since we are, okay, there's no short of time, I can show here itself. So we have the Arduino Uno pin map. So here you can see PC3 corresponds to analog pin 3. Okay, so I am going to connect the positive terminal, that is anode terminal of the LED, to A3. So I need to make it is into red, because normally logic 1 or the positive values, positive potential will be transmitted to red color wire, and the anode is connected to with red and cathode with black. Okay, so after making the connection, you can click on that and change the color to black. Okay, now there is an LED. I can see the code here, and I can just click on start simulation. Okay, so it will be compiled, and you can see the LED is turning on and off. Okay, so here you can see there is an advice mark. So it shows that the current through the LED is more. Now the current that is flowing through the LED is higher than the maximum current that is supported by the LED. Okay, so that is why we always use a series resistor. Okay, so today we have just looked into the development of the program and how to simulate the logic using the Tinkercad. Okay, here we are not bothered about the hardware circuit design. Okay, so this is the simulation of the example that we have discussed. Now you can see that in this code I have used the direct value assignment. You can practice this code, you can modify this code such that you can apply the bitwise operations which you studied. You can try for that before coming for the session tomorrow, so that when we discuss about those bitwise operations etc in the tomorrow's class, it will be more easy for understanding. Okay, so here you can modify the program such that you're only making the third bit of the port C as output. Okay, so what is the change that you have to make in this statement? Okay, similarly when you're writing 1 and 0 to the port, that particular pin using this port C, port X register, how you should allow only 1 to be written, and how you are writing 0 only to that particular pin. Okay, so those changes can be practiced by yourself based on today's class, so that when you come for the tomorrow's session, you will be getting you will be feeling more comfortable with understanding the example programs. Okay. So that's all for today. If you're having any doubts, you can ask it.
We are opening the last session for doubt clearance. All those who have doubt can inquire now. You can either use your chat, or you can unmute yourself and ask.
So there was a question earlier asking that if you want to do a paper. So the major advantage of using this format of programming the Arduino Uno board is that nowadays most of the UG as well as the PG students throughout the country basically focused on practicing the Arduino style, that is using the Arduino IDE and using the inbuilt functions for programs, developing their codes for the project works. Okay, so you can ask your students to practice such embedded programming, so that the students will be getting more into the embedded field, as well as when they go for a job in the embedded market, they will be getting they will be having that skills which is required by the market. Okay, so if there are no further doubts, we may conclude it. In India, we have made corresponding to Arduino, we have the Freedino version. Freedino is the name of the board which has been made by India. It is equivalent to Arduino.
Hello, sir.
Is there anyone else?
Yes,
Shall we
sir.
conclude the session?
Yes, since there are no further doubts, we may conclude it.
Hello, sir.
Yes.
I think someone is trying to ask question. Hello.
Hello.
Yes, ma'am. You
Yes.
can talk. You are
Huh.
audible.
Yes. So I just want to ask you, rather than Arduino, can we use another controller, means for learning purpose?
Yes, we can use any other controllers for learning purpose. Why I have chosen Arduino here? It's not basically Arduino. Basically, I have taken the AVR microcontroller family. Okay, so the concepts which I have discussed here can be applied to any of the AVR microcontroller controllers. Okay, so but this Tinkercad is already having the simulation profile for the Arduino board, Arduino Uno board. That is why we focused on that particular board. Okay, so in the last session, that is on the after tomorrow, I'll be showing the demonstration of a boat, a two-wheel boat, which is been designed to move on specific application. So in that, we are making use of Edmega 2560, okay, which is basically the AVR microcontroller, which is present on the Arduino Mega board. But we are not using the Mega board on our robot. We are having the IC alone together with the other circuitries. And we are going to burn the same program using the AVR Studio to that particular controller, and we'll be implementing the applications.
Okay.
Okay,
Any other question?
No, ma'am. You can conclude.
Okay. Good afternoon, all. With this, we come to the end of today's session. We shall resume the hands-on session tomorrow afternoon. In today's session, an introduction to embedded programming and overview of motor interfacing was given. Topics such as embedded C loops, bitwise, and shift operators, etc., were explained in a clear and concise manner. Overall, the session was highly informative. Now, let me move on to my assigned duty of delivering the vote of thanks. On behalf of EEE department, I thank Mr. Ramesh Sia for accepting our invitation and delivering a wonderful session. I take this opportunity to also thank the participants who actively attended the session. With this, we officially come to an end of day 2 sessions. With hope to meet you all tomorrow, wish you all a wonderful evening. Take care and stay safe. Thank you.